Hello everyone, in this video we'll be looking at the last part of chapter 5, tests for normality. Now 3 types of tests are discussed in the textbook. These are of course tests for normality of the residuals. And by now you understand why this is important. The normality assumption allows us to use the standard sampling distributions that we do to conduct inference on the estimated parameters. Alright, so the first test for normality discussed in the textbook is the histogram of residuals. This is just a graphical device where you plot the histogram of the residuals and juxtapose it against a normal distribution, and you compare the two. If they look similar, then you go ahead and assume that you have normality of the residuals. A second test that is discussed is the normal probability plot. Again, a graphical tool. So you plot the values of the residuals against the expected value of a variable if it were normally distributed. And if you have a straight line in this instance, then it suggests that you have normality of the error term. Now, of course, these days we don't actually graph these things by hand. We do so using computers. And these images show you an example of either of the two tests just mentioned. On the left, you have a histogram. By the way, I borrowed these from the Penn State University website. The image on the left shows you the histogram method, and if you so the idea is that you plot the histogram of the residuals and you check whether it more or less looks normal. And if you squint, in this instance, you can sort of imagine that this is somewhat normal looking, and the idea is just that you have a reasonable approximation to a normal distribution in this case. So even if it's not exactly normal, as long as it somewhat approximates a normal distribution, you might be happy assuming that the error terms are normally distributed for these data. And on the right, you have the normal probability plot. So again, here you plot actual sample values against what you would expect, against the expected value, assuming that the data are, that the error terms are normally distributed. And of course, you're using the residuals here. And if they more or less fall on a straight line, you'll be happy to assume that the residuals are normally distributed. Now, here's an example where that is not true, right? So if you plot a normal bell curve distribution here, the histogram looks nothing like a bell curve, looks nothing like a normal distribution, so you reject the hypothesis that the residuals are normally distributed. Likewise, over here you have the normal probability plot, where again the values of the residuals are plotted against the expected values under the assumption that they are normally distributed, and clearly we don't have a straight line over here. In fact, we have some kind of exponential curve over there. So that we would reject in this instance that we have normally distributed residuals, or error terms in this case. Then the final test for normality that is discussed in this section is the Jacques-Berer test. So this one follows the same process as our previous hypothesis tests, although in this case the test statistic is determined differently, and another difference between the Jacques-Berer test and hypothesis test we looked at previously is that the degrees of freedom doesn't change in this instance. It is always 2, right? Although we do look these values up in the chi-square table as well. So this JB statistic that's given over here, we won't go into how we derive this, but this JB statistic follows a chi-square distribution, okay, with 2 degrees of freedom, always, okay? And it's 2 degrees of freedom because we're effectively testing two data points, 2 parameters, which are also the data points in this case, and those 2 data points are the skewness over there and the kurtosis, okay? So we're sort of doing a joint test of those characteristics when we're doing the Jacques-Berer test. All right, so you start out stating the hypotheses. Null hypothesis being that the residuals are normally distributed, against the hypothesis that the residuals are not normally distributed. Step 2, you calculate the Shark-Berger test statistic using that formula, where S is skewness and K is kurtosis. And then in step 3, you look up the critical value in the chi-square table, and then you compare the test statistic to the chi-square value that you looked up, and depending on the outcome, HO is either rejected or is not rejected. Okay, so let's look at an example of this. So here we have an example which says that for the residuals derived from a sample regression function with a sample size of 50, we estimate skewness of 0.5235 and kurtosis of 2.8899. Conduct the JB test for normality at alpha equals 0.05 or 5%. Okay, step 1, we state the hypotheses. HO is normal. HO, residuals are normal. H1, residuals do not follow the normal distribution. Step 2, calculate the JB statistic. So we just plug in the values for skewness given over there, and for kurtosis over there, and N, don't forget N is 50 in this case. And then we simplify and we get a result of 2.309. Then we have to look up the chi-square statistic, or the critical value in the chi-square table. So we go back to our table at the back of the textbook, and in this case, remember the degrees of freedom is 2 and the significance level is 0.05. So we are looking at a value of 0.05 is this column over here, and degrees of freedom is 2, so it's the second row, and that gives us a value of 5.99147. Right, so which is given on the slide here as well. So the JB statistic is less than the chi-square statistic. Therefore, we do not reject the null hypothesis that the residuals are normally distributed. Okay, so in this case, we can conclude that the residuals are normally distributed. Had the JB statistic been larger than 5.991, we would reject HO and we would conclude that the residuals are not normally distributed. Right, the next couple of slides just go through exercise 5.9 of the textbook. I'd encourage you to attempt these and other exercises, but this is typically one that I would go through with students in a class setting. So I encourage you to attempt this, as well as some of the other exercises in the textbook. It's a good test of knowledge gained. This relates to, well, it gives you data on teacher salaries and spending on public schools for all the states of the US, the 51 states, well, the 50 states and the District of Columbia. And then it asks you to perform a series of calculations. Firstly, just plotting the data. And we see one quite extreme value over here, the top right. Here we've plotted the data, we've put in a trend line as well, and there seems to be an association between teacher salaries and per pupil expenditure as well. Then the next slide gives us the regression estimates for the model, where we regress teacher salaries on per pupil expenditure, and we get these results. Beta 1 coefficient is 12,129, and the beta 2 coefficient, beta 2 hat, is 3.3075. What's nice about the Excel regression output is that it also gives you a confidence limit. So you can see at the bottom right here, a confidence interval for a 95% confidence interval for beta 2. And just above that is a 95% confidence interval for beta 1. We can look at the R squared value over here, which tells us that 70%, close to 70% of the variation in teacher salaries is explained by per pupil spending. What the regression estimates tell us is that one additional dollar spent per pupil is associated with a salary increase among teachers of $3.3, which might sound a little bit high, but of course one has to imagine that typically, even in the US, typically one teacher is responsible for about 30 students, right? So if you multiply that additional dollar by 30, that's only a tenth of that additional spending goes into teachers' salaries effectively. It's back of the envelope calculation. The intercept term is 12,129, and the technical interpretation of that is that when the zero expenditure, per pupil expenditure, then teachers' salaries will be $12,129. This is, of course, annual salaries. And of course, that makes no sense, right? If there's no expenditure on learners, then there's clearly no salaries for teachers. So that number is effectively meaningless in this instance. Question D asks us to establish a 95% confidence interval for beta 2, which is what is shown at the bottom here. Oops. All right, so the 95% confidence interval tells us that, or the confidence limits are given by 2.6 and 3.9 at the upper bound. The question also asks us, would you reject the hypothesis that the true slope coefficient is 3? And of course, given those confidence limits, you would not reject it, right? Because 3 lies between 2.68 and 3.9. Then question E asks, obtain the mean and individual forecast value of pay if per pupil spending is 5,000. But in this course, we won't be dealing with prediction as yet. Browse through these sections of chapter 5 that deal with prediction, but you won't be tested on it and we won't be covering it in the course. And then on the last slide for this chapter, I provide you with some links with some potentially interesting reading or viewing related to statistical significance. Okay, there's a section in the textbook that distinguishes between statistical significance and practical significance, right? So even if we do a hypothesis test on some hypothesized value for beta 2 and find that it is statistically significant, it may be of minimal practical significance, right? It might be a very small value that we are finding to be statistically significant. And the converse can be true as well, right? We can estimate a model, have a slope coefficient that is not statistically significant, yet it is of such a magnitude that it might have some practical significance. As was the case with the intercept term in the teacher salary and per pupil expenditure regression model we just looked at, right? The intercept term was practically meaningless, okay? Even though it might be statistically significant. All right, so take a look at these articles over here. There are two articles. The first two links. The first one is by John Ioannidis, very famous. Well, I'm not sure if he's an epidemiologist in the medical field, but he wrote an interesting paper in around 2005 called "Why Most Published Research Findings Are False." It's not too technical a read. And it's enlightening. It's a thought-provoking read. Of course, John Ioannidis became somewhat infamous during the the COVID pandemic for his research during that time. For those of you who are following the news, you might have seen him appear on some programs with some somewhat controversial views. Then there's an article in, I think this was published in Nature, which also discusses this idea of statistical significance and why it can sometimes be misleading. And for a more entertaining look at these types of topics, there's a YouTube video by a very popular YouTuber whose channel is called Potassium. The videos I've seen by the YouTuber they tend to be quite interesting. Okay, and that is a